Hello. In today's video on electrostatics, we are going to discuss about the ESU, that is the electrostatic unit of the charge, which is a stat coulomb. We'll be beginning with this. We had already discussed about the Coulomb's law in electrostatics, and from that we had also discussed about the permittivity right up to relative permittivity, that is also known as the dielectric constant. Now, to begin with, we have the electrostatic unit of charge, which is known as stat coulomb, and there are actually two units in the CGS system. So this comes under the CGS system, and it is the electrostatic unit. We also have the electromagnetic unit in the CGS system, which is EMU, that is the electromagnetic unit. And in that electromagnetic unit, that's a separate unit, of course, when we are concerned with magnetism. But here, because we are using the case of static charge, the static electricity, that is why we'll be using the electrostatic unit. Now, stat coulomb here is the electrostatic unit, while we also have ab coulomb, which is the electromagnetic, which comes under the CGS system and is the electromagnetic unit. And the relation of stat coulomb with the M case or SI unit, that is coulomb, can be given as follows. That is 1 coulomb of charge is equal to 3 times of 10 raised to the power 9 stat coulomb. We can use this to obtain the value of the electrostatic force constant, that is K, and that comes out to be equal to 1 in case of the CGS system. So in CGS system of units, we have the value of the electrostatic force constant, which in SI was equal to 9 times of 10 raised to the power 9. If you remember, that has a value equal to 1 in the CGS system. We can use this to find this, or conversely we can use the relation between coulomb and stat coulomb to obtain the value of K to be equal to 1. Let's try that. So we'll be going the other way around. We'll be using the value of K over here to obtain this relation between coulomb and stat coulomb. So what that essentially means is that if we have the force between two objects, let us say between two charges, of course, the electrostatic force, that is given by the relation F equals, that is from the Coulomb's law in electrostatics, F equals to K times of Q1 Q2. If two charges being here are equal to Q1 and Q2 separated by a distance r, we have the relation as this, that is from the Coulomb's law of electrostatics. And if we cross multiply the terms and keep K on one side, then we will be having F times of r squared over Q1 times of Q2, the two charges. That means that we have the unit as Newton and meter squared over Coulomb squared. That is the unit, of course, and the value that we get is simply, I left that out over here, that is 9 times of 10 raised to the power 9. That is the value that we are getting here. Now in case of the this is in the SI system. Now in CGS system, we have the value of K to be equal to 1, and that is in dyne centimeter squared over stat coulomb squared. I'll write it as stat C. Even it's ideal to write stat coulomb, but just for explanation I'm using the shorthand notation. So these two obviously are of the same value because we are using the same conditions, so these two will have the same value. So because it's a constant value, so its value won't change even uh, it's the quantity won't change, only the magnitude changes when we are considering different systems of units. So 9 times of 10 raised to the power 9 Newton meter squared per coulomb squared is definitely going to be equal to times of uh, 1 times of dyne centimeter squared stat coulomb raised to the power minus 2. And from that, what we get is 9 times of 10 to the power 9. This is nothing but equal to 1 Newton times of 1 meter squared and 1 coulomb raised to the power minus 2. And the others on the other side, we have 1 times of 1 dyne 1 centimeter squared and 1 stat coulomb squared. Is by dimension analysis that we will be getting this value. Now we do not know that how many stat coulomb make up 1 coulomb. Let's take that for a case over here. So what we are going to do is because we'll be comparing them, we know that this is 9 times of 10 to the power 9. That's okay. What about the relation between Newton and dyne? We know that 1 Newton is 10 raised to the power 5 dyne. So that's the conversion that we are doing on the left hand side of the equation. And also we know the relation between meter and centimeters, that is 1 meter is equal to 100 centimeters, that is 10 raised to the power 2 centimeter, and this is squared entirely. But we do not know that how many coulomb make up stat coulomb, so we'll take it as coulomb x coulomb, or we will say that as x stat coulomb make up 1 coulomb, and that is raised to the power minus 2. We wish to determine that value of x. We already know that, but just for the sake of inquiring from our side. So this is 1 dyne, and then we are taking 1 cm squared, and this is a minus 2 of course, 1 stat coulomb raised to the power minus 2. So if we change the sides, that is we take up those terms and try and cancel them out, what we find is dyne cancels out with dyne, centimeter squared cancels out with centimeter squared, stat coulomb minus 2 cancels out with stat coulomb minus 2. So we'll keep the x as it is on one side, so we have x, and then because we have this 1 over here, we take that 1 below that, and all raised to the power minus 2, we keep that, and we take the other stuff to the other side, that is here we have only 1 squared is again 1, so this top term stays as 1, while what goes down is this 9 times of 10 raised to the power 9, 10 raised to the power 5, because the units have cancelled out. This is 10 squared and squared again, so that is 10 raised to the power 4. X has stayed on the other side, so we'll keep it as such, but it is in the negative power, so in order to make it positive, we just take the reciprocal of this term and we can take that as positive. So x squared is simply the reciprocal of this term, so that means 9 times of, well, for the powers of 10 we have 10 raised to the power 18, so that is the value of x squared. So from that we get the value of x to be 3 times of 10 raised to the power 9, taking the root over. So that is exactly what we had predicted right from the very beginning, that 1 coulomb is equal to 3 times of 10 raised to the power 9 stat coulomb. So that's the relation, because we had used that 1 coulomb is equal to x times of the stat coulomb, and that x is simply 3 times of 10 raised to the power 9, which is exactly what we had discussed earlier. And even though we won't be using the case of ab coulomb in this case, in this segment, we'll be using them in magnetostatics or even in the case of magnetic effects of electric current. So ab coulomb is simply 1 over 10, because that means 1 coulomb is equal to 1 over 10 ab coulomb. So that's the relation between the SI unit and the electromagnetic unit in the CGS system. And because 1 coulomb is also equal to 3 times of 10 raised to the power 9 stat coulomb, we can very easily see the relation, or obtain the relation between ab coulomb and stat coulomb, which also means that 1 ab coulomb will be equal to, the 10 goes to the other side because the two terms on the right hand side have to be equal because the left hand side terms are equal. So 1 ab coulomb will definitely be equal to 3 times of 10 raised to the power, now it is 10 stat coulomb. So this is the relation between ab coulomb and stat coulomb. Now, after having discussed about that, I'll leave you with a question for that. That is, can you tell me what will be the value of the permittivity of free space, that is epsilon naught, in CGS units, that is the electrostatic unit? Having discussed or uh, having the idea about the electrostatic unit of K, that is the electrostatic force constant in CGS systems, can you tell me what is the permittivity of free space in the CGS system of units, that is in the electrostatic unit? Try that and let me know. Okay, now let's discuss about the term called electric field that is associated with an isolated charge. Now, if we have a charge pinned to a point and we know that it's going to impact any other charge which is placed in its vicinity. Now the impact that we get, that is in the form of the electrostatic force, it's either a repulsive force or an attractive force. Now if this is a positive charge, of course, so we place a positive charge in it in any point closer to it and it will get repelled, and if we place a negative charge it will get attracted. The thing is that it has an impact, but the impact is restricted. It cannot go on and on, because as you know that we have already studied the expression for the electrostatic force, and the electrostatic force follows the inverse square law, and from that what we know is that the force is going to decrease exponentially with the distance increasing. The force is going to decrease exponentially as the square of it, and as a result of that what we can tell is that it's going to be near about zero for the distance being taken far away from the given charge. So that means the charge will, this particular charge that I have considered, that will lose its impact, or that will not provide any kind of force to a charge which is placed far away distance from it. So this is more like a limitation in case of a charge being able to impact other charges in its vicinity. And this limitation tells us that it probably provides the force to the other charges in a certain field that it builds around itself, and that is what we term as the electric field. That field extends right up to infinity for sure, but at infinity the impact is very low, almost tending to zero, that we just discussed. For the case of the impact that we are talking about, that is what we term as the electric field intensity. Now the electric field intensity is the impact of the field that the given charge has at that given point. So let's assume that this point over here, the point P, the charge is at the point O, suppose, and this point P is lying at a distance r. Now, in order to determine the impact of the charge that it will have on any other charge that is placed at that point, that is only gettable by considering a test charge, let's say Q naught, which is just to test the impact over there. Then we'll be removing it. So this field intensity, how we define it is that the electric field intensity due to a given charge, so the charge is at point O over here, that is the given charge, and that charge at a distance r from it will have an impact which is given by the equation, the force on any test charge that is placed at that point per unit test charge. And as you can see from the vector notation, that the electric field is actually along the direction of the applied force. So if we are placing a positive test charge over there, then the electric field is obviously acting away from the given charge at the point O. What that essentially means is that if we are taking this equation into consideration, then we'll have 1 over Q naught, and for the expression of force we have K Q naught over r squared, r hat being the unit vector along the direction of the position vector of the given charge Q naught with respect to Q. So from this we cancel out the Q naughts, and we can apply the limit, and we'll get the expression for the electric field intensity at a distance r from the given charge Q. You must note that this expression does not carry the test charge that was there initially, that is Q naught, because that has been removed mathematically. So what that means in terms of physics, what we know from that is that what will any other charge be impacted with if it is placed at that particular point, and now that we know the value of the impact, that is the electric field intensity, due to that fixed charge at the point O. So from this expression what we get is that we can ask what will be the force on any charge. Let's say we place now a charge Q prime at the point P due to the charge fixed at the point O. What will that be? Well, now that we know the impact of the electric field, and we somehow have the relation of the force and the field and the charge, at that point of time it was Q naught, just to test the value of the force. Now having known the impact, we can say that as the electric field at that point is going to remain constant for that fixed charge, so we have the force now, let us say that is F prime on the charge Q prime due to the charge Q, that will be equal to Q prime times of the electric field at that point due to the given charge or due to the fixed charge, which is equal to Q prime times of KQ over R squared R hat. That is also equal to KQ prime over R squared R hat. And this is exactly the relation that we would have obtained from the Coulomb's law in electrostatics. So the relations that we are getting here for the electric field and the force, as well as for the electric field individually, they are essential in order to determine the value of the field intensity as well as the relation that, or the force that any other charge will experience at that particular point due to any given charge. Now from the look of it, what we can also know is that we have the unit of electric field. Now the unit of the electric field intensity is going to be Newton per coulomb, because we have that relation over here, that is force per unit charge. Also, there is another unit that we must consider, that is volt per meter, but that is to be discussed later as we obtain the relation between the electric field and electric potential uh, on the topic of electrostatic potential and potential energy that we will be discussing later. From this also we can obtain the dimension of the electric field intensity. Now the dimension of the electric field intensity, as from the unit we can say that it is Newton per coulomb. Newton is for force, that is ml raised to the power mlt raised to the power minus 2, and as for coulomb, that is A times of T, which is the charge times of the time. So from that we have mlt minus 3 A minus 1. This is the dimension of the electric field intensity. So any given charge, or we can consider charge distributions, discrete or continuous charge distributions, that is to be discussed later, but any given charge will have a certain electric field, and also the case of charge distribution having a certain electric field intensity associated with them. Now talking about charge distributions, we can consider the following cases. Well, the charge distributions are basically of two types, that is the discrete and the continuous charge distribution. As far as discrete charge distribution is concerned, we will be considering different charges at different points, but they are countable. We can count them as 1, 2, 3, and likewise right up to n number of charges considered supposedly. And suppose we have a charge q1 over here, q2 over here, q3 over here, and it extends right up to qn. So there are n number of charges distributed over a given space, but they are a handful. We are counting them. Now consider the case of electrons. Now the electrons that are present in atoms, and 1 mole of a substance has Avogadro's number of atoms, that is 6 times of 10 raised to the power 23. So it's of that order. And even if we consider the case of metals and we take out one of the charge or one of the electron, the outermost electron is always available for any kind of conduction in it. So the outermost electron taken out from a metallic atom, and a few grams of it constitute the Avogadro's number of atoms. So even if we take out one electron, there will be Avogadro number of electrons in those few grams, and that many electrons cannot be termed as discrete system because they are the number is quite huge, and as it is that we cannot determine the position of an electron or even its momentum, thanks to the case of Heisenberg uncertainty principle, we know that it is not easy to determine, or it is next to impossible to determine the position of the electrons. So what we do there is that we consider the continuous system, even if they are countable, but still the number is pretty huge, and that is why we consider them as continuous system, and we consider them to be distributed over probably a line uniformly. So these are uniform charge distributions, or over a given area, or over a given volume. The volume need not be necessarily a cube. The area need not be necessarily that of a square or rectangle, but still, just for the sake of understanding, we can say that the charge, we can take the electrons, or we can take the charge to be any given charge q, to be distributed uniformly over a given length L. In that case, we say that the charge per unit length is the linear charge density, and the linear charge density in this case is Q over L. Now if we are considering the area is usually the surface area S, and a total charge Q is distributed over that entire surface area S, then we term it as the surface charge density as sigma, which is equal to the charge per unit surface area. And if the charge is distributed uniformly over a given volume, so that the charge density is uniform in that case, so we have the volume charge density, that is denoted by the letter rho, and that is equal to charge per unit volume, which is uniform in this case as well. So using these cases of charge distributions, we can determine either the force that they apply on different charges placed close to them, but firstly we can also obtain the case of the net electric field intensity. Now how do we do that? Well, as far as the discrete system is concerned, to begin with, first we'll be discussing the discrete system so that we can have a clear idea about what we are going to do. So if we have a point supposedly where we wish to determine the net electric field intensity, how do we do that? So this is the point P, and we wish to determine the net electric field intensity due to the system of discrete charges that are present over there. Now we know that it will have obviously different positions with respect to different charges that have been provided. So with respect to Q1, supposedly it is lying at a distance of R1, so that the position vector is directed along that line, and so the electric field due to the charge Q1 will be along that line. We'll consider the cases of lines of force later in the video after this. So this is E1, that is the electric field due to the charge Q1, which is from which the point P lies at a position R1. With respect to Q2, supposedly the point P lies at a position R2, and as a result of that the electric field is directed along that line is E2. Similarly for Q3, to make the figure look prominent, we will be avoiding the charges in between, and I'll jump right over to Qn. So from Qn, again the position, let us say, is Rn, and along that line is the impact of the electric field that is observed, that is the electric field intensity, and let us suppose that is En vector. Now there is a principle of superposition that you might have come across in case of the addition of the waves that was in the chapter of waves and oscillation, and it's a similar kind of principle that we'll be using over here as well. So the principle of superposition states that if we are to determine the net electric field at the point P, then the individual electric field intensities of the given charge distribution, that is the discrete charge distribution in this case, is equal to the vector sum of the individual field intensities that we have over there, which extends right up to En. But it's not only that, the individual electric fields will be acting independently, because there will be the case of the electric field intensity or the force between the charges themselves, because there are a lot of charges present over there. So you may consider the case that what about the force or the field intensities in between the space? Well, that is not to be taken into account in case of the principle of superposition, because the principle of superposition states that the net field intensity is equal to the vector sum of the individual field intensities due to the individual charges acting at that point, but they must be acting independent of one another. The force or the field in the points between them need not be considered. If they are having some impact on one another, that is to be left out, that is not to be taken into account. Now, what is the case that we get if we place a charge at that point P? Let us say that we place a charge Q at that point. Now, the Q will be impacted by the net electric field. Obviously, it will be impacted by the individual fields as well. But now that we know that the individual fields add up vectorially to give the net electric field, so we'll have a net force that it will be acted upon by the individual forces taken into account. So that is equal to Q times of E net, because that is the net electric field. And if we use the expression over there for the net field, that is E1 plus E2 right up to En, then we use the distributive law. So we multiply the Q to each of those terms. Then what do we find? Well, Q times of E1 is nothing but the force that it would have been acted upon at that particular point due to the fixed charge Q1. And also Q times of E2 is the force that it will be acted upon due to the charge Q2. And similarly, right up to Qn, the force due to Qn on it. So eventually what we are getting is that the net force is also obeying the principle of superposition, which states that the net force acting on a given charge due to a system of discrete charges is equal to the vector sum of the individual forces which are acting independently, of course. As I said, they will be putting some force on themselves in between amongst themselves as well, but that is not to be taken into account. What we need to consider is that the net force that will be acting on the given charge in question. Now, if we put the charge Qn under scanner and we say that this is a free charge which will be acted upon by the force due to all the other charges, then those charges will be forming the discrete system and their force will be acting on Qn, and at that time we'll be considering the position of Qn with respect to the rest of them, and we'll be obtaining the field at that point, or even the force directly can be calculated at that point, the net force, that is. So that's the case about the discrete charge system. Now what about the continuous charge system? Now the continuous charge system cannot be taken in the manner that we did for the discrete charge, obviously, but because the addition is not going to help in this case, this kind of addition, because we have the numbers over here right from 1 to n, this kind of addition is not available in these cases. So what we do is that we just replace the addition with a more sophisticated integration. So what we do is we integrate the field due to a small segment over the entire length, or probably over the entire surface, or the entire volume, as the case may be. That is, if we are considering a linear charge distribution, we will consider the force, we will consider the charge per unit length, and then we'll have that we'll be considering a segment of it, let us say dl, and due to that we wish to determine, supposedly here's a charge distribution, it has a length L, we'll consider a length dl from it, and we will be obtaining the electric field at a given point P. Then we'll be integrating it over the entire length right from the bottom to the top, and that is the process. So lambda dl will be the charge for that small length, and that will be integrated over the entire length, k times of the charge over distance, probably over here x squared, that is to be integrated in this case for the entire length, let us say is L over here. Likewise for surface and for the volume, we'll be using the cases of sigma ds k over the entire surface over the distance squared, and also for the volume k here is obviously the electrostatic force constant, rho dv for a small volume v dv, and the distance probably is x in that case, and that is to be calculated over the entire volume. So this is how we'll be calculating the net electric field intensity at a given point due to a charge distribution. And probably for probably the case of force, we'll just use this case, that is the force will be equal to q times, suppose we place a charge q over there, then the force will be equal to q times the net electric field that is acting on that at that point due to the given charge distribution. We'll be trying a few numericals as well as examples from the topic that we just discussed. It will be in the numerical segment of the electrostatics, probably in the assignment segment. I'll let you know. So that's all from this video. Stay tuned for the next one. Till then, thank you for watching.